Swayam Prabha. Digital India. Educated India.
Welcome to this another session on ultrasonic machining under the course Advanced Manufacturing Processes. In the last session we have discussed about the basic features in ultrasonic machining process, the machine used and its subcomponents. Also the suitability and tooling was also discussed briefly. In this session we will mainly study about the tool holders and tooling requirements, the mechanism of material removal, process parameters that affects the quality of the machined surface in ultrasonic machining, then some variants in ultrasonic machining process as well, like we have discussed in some other processes, then applications of ultrasonic machining process. Let us look at the tool holder, which is considered to be one of the important components in this system. The shape of the tool holder is generally cylindrical or conical or a modified cone which helps in magnifying the tool tip vibration. Thus, the shape of the tool is determined according to the optimization of the tool vibration. In order to reduce the fatigue failures, it should be free from nicks, scratches and tool marks and polished smooth. Now, let us see the design of the tool. The tool material should be tough and ductile. This has been already told in our earlier sessions. Then accordingly, low carbon steel and stainless steel, these are some of the materials that give good performance as far as the ultrasonic machining is concerned. Tools are usually 25 millimeter long in its size and its size is equal to the hole size minus twice the size of the abrasive. This is basically like this. If this is the hole to be produced, then the tool should be such that this is the hole size and this is the difference sidewise . This should be the difference here. This is the tool and this is considered to be the workpiece and this is the size of the say tool hole diameter. Then tool diameter should be say this is D tool and this is D hole. It should be one diameter H side of the abrasive particle. This is abrasive and this is abrasive. So, this is average, you can say average abrasive diameter. So, therefore, so that the abrasives can enter and the abrasives here after doing the work or cutting here can come out through this. So, this is basically followed while designing a tool in case of USM. Mass of the tool should be minimum possible so that it does not absorb the ultrasonic energy. Then what are the other requirements of the tool? It should have high wear resistance, should have good elastic properties, it should have high fatigue strength, as it will be continuously subjected to fatigue kind of loading under very high frequency. Then it should have optimum strength, because this will have to withstand the impacts of the abrasive particles as well, and abrasive particles are of usually very high strength materials, hard materials like silicon carbide or boron carbide, etc. And then it should have also optimum hardness. Let us see a schematic representation of this USM apparatus like this. So, this is the apparatus is in the screen. Here basically this is the workpiece to be machined, either drilled or cut or whatever, and this is fitted on the work table. This work table will be in generally it will be part of the entire machine setup, it will be integral part of this machine setup, and in some cases this work table can be made the computer numerical control as well, so that we can have a better control or numerical control on the size of this or on the movement of this workpiece. Then this is the slurry system, where the pump and the filter and the stirring arrangement will be there, and this slurry will be made to flow to this machining zone with the help of some hose arrangements and the pump. This can be the flow rate can be controlled by proper control here. Then apart from this, the main structure of this setup is something like this. So, wherein the electrical power will be provided and the transducer will be responsible for converting this electrical power into the mechanical vibration. This mechanical vibration will be further amplified, and this sonotrode will be responsible for coupling this mechanical vibration to the tool tip, and finally we will be observing the net result, that is the oscillation, mechanical oscillation at this tool tip. So, this arrangement is for coupling, then conversion of electrical energy into mechanical energy, and then the amplification of this mechanical vibration to a desired level, and this vibration can also be controlled by appropriate control mechanisms of this electrical power and so on. Further, along with this vibration or the frequency of oscillation, we can also control the amplitude at which it is vibrating. That arrangement can also be made in this control system. Coming to the movement of the tool in USM process. So, during one strike, the tool moves down from the most upper remote position with a starting speed at 0, then it speeds up to finally reach the maximum speed at the mean position. Then the tool slows down its speed and eventually reaches the 0 again at the lowest position. When the grit size is close to the mean position, the tool hits the grit with its full speed, and smaller the grit size, the lesser will be the momentum it receives from the tool. The forces induced due to vibration are shown in the sinusoidal waveform. The areas under the curve can be assumed to be triangle to enable solving it in the form of an equation. This is explained in the following figure. So, this is how the variation of the force will take place. So, here force will be maximum, and this will move from maximum to minimum, and this is the delta t, and this will be approximated with a triangular shape. And this is the schematic of the tool position with respect to the abrasive as well as the workpiece. So, this is considered to be the lowermost position an abrasive can have, where the tool can hit it before going inside the or before making the indentation on the workpiece. So, this is the topmost position where the tool will start getting accelerated, and this is the mean position where tool will attain its maximum velocity. Then again it will start decelerating, and when it reaches here, so this is the minimum position it it comes to, and then it starts pushing the abrasive material against the workpiece surface here, and the abrasive will move through or penetrating this work material hereafter. Thus, if we go into the mathematics of this, what happens? So, after simplification, the force equation reduces to be something like this. This is F equal to 1 upon T, then integration of F I, F is the force at a time instant T, which is integrated from 0 to time T. The T we have seen in the previous slide. So, T is this duration, this is delta T, and this is T total, one cycle of this. So, within one cycle, what is the variation of the force? So, from this diagram, the position A means the tool is still not in touch with the abrasive grain, and the position D is it has pushed the grain to the lowermost point where it absorbs the workpiece. So, these positions are shown here. This is the lowermost position and this is the topmost position A. Now, let us have a look at the abrasive slurry, detailed look on it. The recommended slurry to be used in this process is a mixture of abrasive particles and liquid. This liquid can be water, which is most widely used, which is low cost, easily available, and environment as well as the operator friendly, and of course, kerosene can also be used. This is also a low viscosity fluid, and therefore, this can also be used. Of course, fire hazards or health hazards are associated with this liquid. The slurry is pumped across the tool face. The slurry pump is a part of the machine system, as we have seen already. The properties required from the transport medium of abrasives include low viscosity, good wetting, and high thermal conductivity. This is because while impacting, there will be a localized heat development, where the abrasive materials will hit the workpiece. There will be a localized development of the heat or temperature rise will be there, and this heat should be taken away by this medium quickly. Otherwise, the softening of the material will take place, softening of the tool material may take place, and that will bring down the efficiency of the process further. As we know, this process is basically works on the brittle fracture of the material, and if the material gets softened, there will not be the brittle fracture condition prevailing anymore. Water is a recommended medium for abrasive transportation, which generally meets most of the process requirements. Now, let us look into the process parameters that affects the USM process, ultrasonic machining process. The determination of accurate process parameters which affect performance of ultrasonic machining is hard, as it works under multiple factors. Already we have seen there are as many as 4 known mechanisms that could take place during ultrasonic machining. Therefore, what exactly the parameters, number of parameters, and to what extent they are having the influence, quantifying them, and quantum with which they are acting on the process is very difficult to determine. So, the evaluation process or the assessment of this is very time consuming, very expensive, and I am afraid at most of the time we do not have the requisite equipment also for that. The geometry and material properties of the workpiece and the tool make the system further complex to ascertain its performance characteristics. However, the performance of ultrasonic machining to some extent is decided by the machining rate, the machining accuracy, surface finish, and tool wear. Machining rate is always important as far as the productivity is concerned, and as far as the quality is concerned, machining accuracy and surface finish both are very important to meet the standard, to meet the quality, and to meet the expectation of the customers. These parameters are very important. And of course, another operating parameter is like tool wear, which is unseen to the customers, but which is very important as far as the operation is concerned. If tool wear is very high, the downtime of the machine will be very high, and the cost will be cost corresponding to this will be very high. Therefore, low tool wear will be indicative of better performance of the process. The process parameters in ultrasonic machining affecting the qualities of the machine surface can also be represented in an Ishikawa cause effect diagram like this, in which 4 different major categories of parameters are shown. Those are abrasive slurry based parameters, then machine based parameters, tool based parameters, and workpiece based parameters. In abrasive slurry based parameters, types of fluid, size and shape of the abrasives, these are important. In machine based parameters, frequency of vibration and an amplitude of vibration, then the static load, these are important parameters that affects the quality or the performance. Then as far as the tool is concerned, as we have already discussed, tool material is very important. So, the properties of the tool material is important criteria, then shape of the tool material, then the mechanical properties of the tool material, strength etc., hardness, and then the surface. Then workpiece related parameters are like work hardening, then fracture properties, hardness, etc. These process parameters affect the performance of USM can be arranged in this 4 categories like abrasive slurry, machine, tool, and workpiece based parameters. In these machine based parameters, frequency and amplitude of ultrasonic vibration is most important as far as the working of the entire machining is concerned. Then static load, of course, which influences the material removal rate, this is also very important. Then workpiece rotation, in some cases the workpiece also can be made to rotate, so that the flushing becomes more effective and the corresponding material removal becomes more. Then tool head also can be made to rotate, again to enhance the capability of the machine or the performance of the machining process. Then abrasive slurry characteristics should be like the type and size of the abrasive particles, their hardness, then the type of the fluid used as a carrier to form the abrasive slurry, and the concentration of the abrasive particles in the slurry. These things are very important as far as the characteristics of the abrasive slurry is concerned. As far as the workpiece properties are concerned, the following properties affect the performance: the hardness, fracture characteristics, strength, work hardening tendency, and fatigue properties of the work material. These are some of the parameters that affect the process performance. Like for example, if the hardness of a work material is less and it is more ductile, then the performance will come down. As we know, this entire material removal depends mostly on the brittle fracture of the material, and in case of ductile material, the material will tend to flow rather than fracture, and therefore, the material will flow sidewise rather than getting removed or sheared fracture from the workpiece original material. Then let us see the tool material properties and the tool geometry. The shape of the tool, whether it is a solid tool or it is a hollow tool, in both the cases the performance will be different. The hollow tool will tend to get worn out very fast, whereas the solid tool will give better tool life as far as the wear is concerned. Whereas in case of hollow tool, probably if we are going for a through hole, then it can give better result, as the machining area will be less, and therefore, the entire tool and the machine will experience less load in due course of time. Similarly, the mechanical properties of the materials used in tool making, that is also important as far as the tool material and tool geometry is concerned, and this will affect the process performance. Now, let us look into the capabilities of this ultrasonic machining process. The USM process is capable of machining any materials regardless of their conductivity. The USM process may be applied to machining semiconductor such as silicon, germanium, etc. In fact, in the semiconductor industries, this ultrasonic machining process is very widely used. Ultrasonic machining is also suitable to precise machining of brittle materials. This has been discussed repeatedly so many times. Then it can drill circular or non-circular holes on very hard materials. Less stress is developed because of its non-thermal characteristics. Also, USM does not produce any abnormal surface due to electric, thermal or chemical effects. Excellent surface qualities with average roughness less than 0.2 micrometer can be achieved with normal machining conditions in this process. The USM process can be controlled using intelligent control algorithms, thereby safety can also be ensured. Protection of workpiece and tool can be achieved because of reduced contact forces and low thermal stress. Self-sharpening diamond tools guarantee high removal rates at low contact forces and long service life. Water as coolant and cleaning medium with excellent ecological compatibility can be achieved. As we know, water is the main working fluid in this system, ultrasonic machining system. Now, let us look into some limitations as well. Ultrasonic machining has low material removal rate. This is inherent to it. Machining area and depth is restrained in USM. Then the cost of machining is high. Regarding the restraining of the machining depth, we can see it like this. So, this point can be explained like this: if a hole with high aspect ratio is to be drilled with this process, say this is the workpiece, my workpiece, then the tool should move like this by a considerable distance inside this workpiece. So, this is the workpiece. Now, there will be difficulty in these abrasives coming through this and getting flushed out like this or a similar case. Therefore, if the fresh abrasives cannot enter into this zone where the machining is taking place, the machining is taking place here only. Now, if the fresh abrasives cannot reach this zone, then the cutting performance will not be good. And not only this abrasive should reach this position, but also this need to be flushed out from this position, so that a fresh cutting edge can come into this, enter into this. Therefore, this is inherent, we can say, a defect or inherent limitation of this process, where very high aspect ratio holes cannot be drilled in an efficient manner. Under ideal conditions, penetration rates of 5 millimeter per minute can be obtained. Power units are usually 500 to 1000 watt output units, and in this process specific material removal rate on brittle material is 0.018 cubic millimeter per joule can be obtained. Normal hole tolerances are 0.007 millimeter and a surface finish of 0.02 to 0.7 micrometers can be obtained. The following figures show some of the capability of this process. So, here this is a strip which is having 1.2 millimeter thickness only, and within this 1.2 millimeter thickness, holes of 0.4 millimeter diameter are being drilled using this USM process. This talks about the performance or the capability of this process, that such a small holes can be drilled effectively on such a small strip of material. Again, this is another application or machining example in which only 50 millimeter diameter material or a strip having 50 millimeter width, and here number of slots are being cut using this ultrasonic machining, and each slot measures 0.64 into 1.5 millimeter in dimension. Thus, this also talks about the versatility of this process and its usefulness in various small machining applications as well, or micro machining applications as well. We will see some of the developments in micro machining using this micro ultrasonic machining in another session. So, this is a typical hole being produced by this ultrasonic micro machining. So, here the very small holes are being drawn. Now, let us move into the effect of process parameters. We will look into the major process parameters which are being investigated very widely, and the effect of these parameters on surface produced as well as on the material removal rate we will try to explore. So, here as far as the feed force is concerned, so this is the characteristic actually this happens, and this is what is theoretically it should look like. That means, as the feed force increases, the material removal rate also linearly should increase at the same rate theoretically. However, it was found that beyond a certain optimum force, feed force, this slightly drops down. That means, this indicates that there is an optimal feed force to be applied, and if the feed force is higher than this, then probably the crushing of the abrasives that take place instead of machining of the workpiece. So, that may be the reason why this material removal rate comes down with very high feed forces. And these are another two characteristics as far as the vibration frequency is concerned and as far as the amplitude of this vibration is concerned. How do they affect the material removal rate in this? So, here also theoretically, if we see as the vibration frequency increases, the material removal rate should increase, and in fact it increases, but not at the same rate. It is bit sluggish. As the frequency is increased, the material removal rate does not increase at the same rate, it is bit sluggish. However, as far as the amplitude is concerned, so here also in this case also with amplitude, increase in amplitude, the material removal rate increases, and if we see along with that the feed force, then with feed force this rate, material removal rate further increases. If we increase forces, feed forces like this, then the rate of material removal becomes higher, still higher with increasing amplitude. These figures show the characteristic of material removal rate with respect to grain size and abrasive concentration in the slurry media. The grain size also we have seen a very peculiar situation, like up to a particular optimum grain size, the material removal rate increases with grain size. However, beyond that grain size or grain diameter, we can say for in this case it is something like this, the material removal rate do not increase appreciably, rather it remains almost same. That means, there is an effective limit of the grain size also which we can use in this process. Maybe beyond certain sizes, the grains will not come into the actual working zone or the cutting zone will not reach there, and therefore, the cutting will stop. Then as far as the abrasive concentration is concerned, so this is also showing that as abrasive concentration increases, that means the percentage of abrasive present in a particular volume of slurry media, then the material removal rate also increases. However, again the same thing happens beyond a particular optimum level, the increase ceases or the rate of increase comes down appreciably, rather it shows a tendency of saturation. As we can see from here, it shows some sort of saturation tendency. This is because as the concentration increases, then rather than the abrasives hitting the work surface, they themselves hit and the causes the fracture on them. This can be explained something like this. If this is the workpiece and these are the abrasives, and if the abrasive concentration is too high in the cutting zone, this is tool which is hitting these abrasives in this way, or you can say this is oscillating like this, then instead of these abrasives hitting this work material effectively, this each of these abrasives, so these are nothing but abrasives. So, they themselves will hit each other. So, like this. So, this will hit this will hit this, then this will hit this probably, and then these abrasive materials will get fractured into smaller parts, rather than they are doing work on this work material or hitting this work material, they themselves will get engaged in hitting each other, and therefore, the cutting efficiency or the material removal efficiency will come down appreciably, or at least we can say they do not, it does not show any increasing tendency any further. So, this is what is explained by this saturating tendency of these curves. Next parameter is the viscosity. We are talking about the slurry. Slurry is one of the important component in this system, and if this particular characteristic shows as the viscosity increases, the material removal rate decreases, which is quite possible, because as the viscosity increases, the movement of the particles, the abrasive particles in this medium becomes sluggish. However, as we know, the efficiency of cutting will depend upon how fast these abrasive materials can hit the material in that cutting zone. Therefore, if the viscosity increases, then this abrasive particles cannot move faster, and neither the debris produced inside the cutting zone can be taken away faster, nor those abrasive particles after getting hit by the tool can move towards the workpiece faster, and therefore, the material removal rate will slightly come down. Whereas, with very low viscosity material media, we can see very good or very high material removal rate, because of the reasons I have already stated. The next parameter is the mean grain diameter. This also already we have discussed, but let us see how does this grain diameter parameter or the abrasive size. Mean grain diameter is nothing but it indicates the size of the abrasives, and therefore, as the size of the abrasive increases, the average roughness obtained on the machined surface also increases. That means, the surface quality becomes poorer. This is quite obvious. So, higher grain size particles means it will cause higher indentation on the material, and the debris produced or the fracture that will take place over the area will be much larger, and therefore, the correspondingly the roughness of the surface that is being machined will be much higher. That means, that is indicative of poor surface. This particular characteristic is shown for tungsten carbide material and as on glass material. A glass is still brittle material, it is relatively more brittle than the tungsten carbide, and therefore, it shows even poor surface finish with increasing diameter of the abrasive particles. But tungsten carbide being relatively less brittle, it shows little a better or good response towards higher grain size even. So, as already we have discussed, the surface finish in USM depends on the hardness of the workpiece or the tool of the average diameter of the abrasive grain used. The process utilizes the plastic deformation of metal for the tool and the brittleness of the workpiece. This combination works good for this particular process, and as we have seen, the grain size is as far as the surface finish is concerned, higher grain size is not good, and as far as the material removal is concerned, so larger grain size is better, or we can get better material removal rate. As far as the machining time is concerned, it depends on the frequency at which the tool vibrates. Then on the grain size, I have been already discussing about this grain size, importance of grain size as far as the MRR is concerned and as far as the surface finish is concerned. Then of course, the hardness, which must be equal or greater than the hardness of the workpiece, and then the viscosity of the slurry fluid. Regarding the viscosity also we have already discussed that lower viscosity generally gives rise to better material removal rate. The less viscous and slurry gives faster machining, as the it can carry very easily the abrasives and the debris from the machining zone. Considering the hardness, the common grain materials are silicon carbide and boron carbide. These two materials are found to be very good as far as the hardness is concerned and as far as the effectiveness of these materials in machining is concerned. Now, let us have a quick look at the types of the ultrasonic machining. So, there are two types: stationary USM, in which tool is vibrating, but there is no rotation induced in it, whereas the other is rotary USM, known as rotary USM or RUSM, in which tool or work anyone can be vibrating as well as rotating also. In stationary ultrasonic machining, this is a common process. So, this is in most of the industrial applications we will find this stationary type of ultrasonic machining, and this we have been discussing with reference to the stationary type only so far. And in this only the tool vibrates while the workpiece remains stationary and it is fed in the required direction. On the other hand, let us see in the rotary ultrasonic machining. In rotary ultrasonic machining, the USM equipment possesses a rotary movement either at the ultrasonic head or at the work table. So, this is used for mainly for drilling, milling or say threading operations. In rotary ultrasonic machines, the combination of rotational motion and axial vibrations of the tool reduce the friction between the tool and the workpiece material. This is the advantage of rotary ultrasonic machines, and the spindle speed used in this is variable and it can be between anywhere between 0 to 8000 RPM, and this rotation along with the ultrasonic motion enhances the cutting action of the attached diamond plated or impregnated tool. It also provides uniform tool wear, a high degree of hole roundness and rapid removal of material from the cutting zone. Therefore, it is as good as far as the higher productivity is concerned and better finish is concerned. Let us see the benefits of the rotary USM. The combined action of the rotary ultrasonic motion plus a water coolant produces a self cleaning action. Because of the tool head is rotating, it will be washed continuously, get washed continuously, and then efficient cutting at a higher tool pressure than with conventional machining. Lighter tool pressure is advantageous for drilling small diameter holes, long deep holes and adjacent holes that are very close to one another. Reduction in friction between the tool and the workpiece that results in extending diamond tool life and reduces stresses caused by conventional diamond tool machining. So, these are the advantages of having rotary ultrasonic machining. Now, in the end, let us summarize what we have discussed in this particular session. We have seen the details of the ultrasonic machining process and working principle, the process parameters in details and their effect in various performance parameters like material removal rate as well as the surface finish or surface produced. We have seen also the types of USM. There are two types of USM, rotary USM and stationary USM, and we hope this session was very interesting and enjoyable. Thank you.